Got it. Okay, thanks very much for inviting me over again. Always fun to get a chance to talk with you folks. Um, so when Ron asked me if I could give a talk, it happened the same day I actually saw a program on Nova, and some of you may have seen it too, where they were talking about some of the ways people are searching for life in the universe. And this actually got me thinking about a really an ongoing conversation that Joanne and I have had now for many years, often coming down on different sides of this, where we've kind of asked the question, so how are we going to find life? What would be the first way for us to find life? And I think it's time to really start talking about it in terms not just of looking at one way, but really looking at the range of different methods we have for searching for life in the universe, because it's really quite amazing now what that looks like. So I'm going to share my screen and we can dive right into this here. Do that. All righty. So get this started up. Okay, so I'm treating this as a race now. The race to find life in the universe. And I think it is a race now. I think we're really, and I'll try to sort of convince you why why we can look at it that way. So here's the basic outline. We'll start out just talking a little bit about in general about searching for life in the universe. I want to distinguish between two different types of life, because that is kind of very much shapes the way people think about looking for life in the universe. And then I want to talk about four different broad techniques and look at some of the details on each one of them. One thing I should say about this talk, as I was working through it, I'm probably going to you're probably going to feel I'm going kind of fast, simply because almost every slide in this could be a talk by itself. There really is a lot of detail that I'm kind of going to gloss over just so that we can have time to cover as much ground as I'm going to here today. So let me dive right in, talk about searching for life here. And as you all know, the idea of looking for life in the universe is something that has been a fascination for the public for a long time. I mean, probably more than a century now, at least. We go back to the beginning of the 19th century and people searching for life on Mars. And this is something that has always had a big public interest. On the other hand, in science, it comes and it goes. There have been definitely decades when if you said you're looking for life in the universe, that was just about a career killer. And then there have been other times when, yes, it was a very respectable thing to do. Right now, it's very respectable. And really over the last 25 years, which is kind of sort of parallels my career, actually, this is a topic that has become more and more respected within science. When I started in grad school back in the late 80s and early 90s, if you were interested in this, unless your name was Sagan, you didn't talk about it very much. There really weren't a lot of people who were willing to talk about that much. But that has changed, and that's changed a lot. And you can point to a few very specific things that have happened in this period that have done that, have helped cause the scientific community to take this a lot more seriously. One of them is this little rock, ALH 84001. It's a meteorite. It was found in Antarctica, and eventually people realized that it was from the planet Mars. Now, that by itself isn't unusual. There are a lot of meteorites that have come from Mars. We now know. We found a number of samples, at least. But what was really exciting about this one was that a group of very respected scientists studying this said, we think we're seeing evidence that there was something alive in this, that there are both chemical and physical evidence for fossils in this rock. And that was huge. Okay, this is 1996, and it was an amazing announcement, and it really sort of it changed a lot of the picture of what people thought about the possibility of finding life. Now, in the period since then, a lot of that evidence has been put into question. At the very least, you could say, yeah, there are actually other explanations for what they were seeing there. Nonetheless, as I say, this really sparked a lot of interest. Another thing happened in 1996 that was also very relevant to this, and that is we started finding exoplanets. We started finding the first planets around other sun-like stars. And for those who remember that process, it started out, you'd find one, and then you hear an announcement about another one, and then there may be two. And then the Kepler launched. The Kepler mission, of course, was a planet finding mission using transits, and it started announcing not just one or two, but 1,000 or 2,000 new planets they would come out with. So that we now can seriously talk about the statistics of planets. We can make some reasonable estimates about how many planets are out there, how many maybe Earth-like planets are out there, and how many Earth-like planets are even in the regions around their stars that we might call habitable. And that's amazing. Okay, this is, so people can have, because of this, are now able to seriously answer the question, well, are there even planets out there? Is there any chance that there are planets in the right place? The answer is yeah, because almost every star you see in the sky has got planets around it. That's the really big announcement here, and that are coming to realize that has really made the idea of wondering if those are habitable, made that much more respectable than it used to be. Another thing that's happened, and this is a much more recent event, was 1I2017 U1 Oumuamua. And I've talked with you folks about this one. So this was the first hyperbolic asteroid. This was the first object that we know for sure came from outside of our solar system, passed through the solar system, and then moved on again. And it got people seriously thinking about, okay, first of all, yeah, we can find things from out of the side of the solar system coming through, and we could we are actually connected with this larger universe. And so, as we'll see later, this is another piece of this puzzle of looking for life in the universe. And indeed, this one caused a little bit of speculation about whether it could, in fact, be a spacecraft. We don't think it is, but it's getting you into that territory here in terms of having to ask about that. The other thing that's happened over the last 25 years was that NASA discovered money, to be honest. I mentioned ALH 84001. When that meteorite was announced in 1996, at that point, there was a hiring freeze at NASA, agency-wide. They could not hire any new people. Within a month of that announcement happening, the hiring freeze was broken. NASA was hiring new full-time scientists, particularly people working on things related to origin of life, origin of solar systems. They started a whole new program, the Origins program. Why? Because suddenly they were getting money they didn't have before. And they were getting a lot of interest from the political side saying, this is something, yeah, we want to pursue this. And NASA has learned that lesson very well, so that now, if you look at the NASA website, you can find the NASA exobiology site. This is now a major goal of NASA, is searching for evidence of life in the universe. So it's gone from being something that is, you didn't even really want to talk about, to being, a major source of funding, honestly, in astronomy research now. So that's why searching for life has become respectable. And so I feel then that because of all of this, the race is now on. And it's reasonable to start asking not just will we find life? I mean, that we still have that basic question, but where will we find life and how will we find life in the universe? Because if it is there to find, we are now looking on many different fronts. And you can definitely say there's a bit of a competition between all these different routes to who's going to be the first ones to find that evidence. So let's talk about what we mean by finding life in the universe. And as I said, I want to divide this up into two kinds of life. First of all, there's any life. And yeah, that's a tricky thing to define. And I'm not going to pretend, I'm not going to attempt to give you a definition of life. You could say, well, anything biological, but that's kind of circular anyways. It's any living organism. And we have some requirements that we think we can place on living organisms. Living organisms definitely require energy. They definitely require the raw materials that let you make the kind of complex reproducing sort of things that we consider to be alive. That generally means something carbon-based. And they need a liquid to mediate, to act as the fluid in which all that chemistry can happen. And water is for life on Earth is the material that fills that role. There may be other materials, but water certainly looks really good. And I'll mention alternatives at one point here today. So those are the kinds of things that help constrain where you might look for life. You want to be looking for that combination of things. When we talk about any life, we really mean any life, okay? Algae would be fantastic, okay? Bacteria, great, okay? When we're talking about any life, that's really, as much as anything, what we mean. And when you look at the history of the Earth, up to now, most of our planet's history has been dominated by single-celled organisms. So that's really what you want to be thinking of when we talk about looking for any kind of life. I really am talking that basic here. But single-celled organisms can have global effects. That certainly happened on the Earth. The oxygen we're breathing is a direct result of that. So this can be, so you don't want to underestimate these things just because they're small. So you definitely want to look at this as a thing that can affect an entire world, which is why we think we have a chance of finding some of these. So this brings up a term that I want to introduce, and that's what we call a biosignature. And in this field, the term biosignature means any signal, anything we could receive, maybe a spectrum, maybe something about a color, something that we feel could only be done by a living organism. That's a biosignature. And so that's one of the key things. I'll mention that word biosignatures as we go along here. That's usually what we're trying to look for, is something that is a clear hint that yes, there's something alive there. Okay, so the other category of life I want to talk about is intelligent life. And intelligent life is its own tricky thing to define. Usually it's defined in terms of whether of something that uses technology. And that's okay, that's great, that that covers a lot of things. For a long time, the search for extraterrestrial intelligence was sort of criticized for really being the search for extraterrestrial electrical engineers, and that was really what you were looking for, because they were looking for signs of radio signals. And so, you have to try to think broadly about this, but that is a limitation. We can't see any and all technologies. There's no way. And so you have to think about what technologies you really can see and what limitations that puts on the kinds of life you might actually be able to find. Okay. Again, though, technology can have global effects, and in some cases, even beyond the global effects. And so this is some of what people are looking for when they're looking for signs of intelligence. So that brings up, again, the equivalent to biosignatures here, what we call technosignatures. And then again, this is a signal that, as far as we could tell, could only be produced by some kind of technology, does not happen naturally. And so that's really what the folks who are looking for intelligent life, what they're they're actually searching for. So let's, having seen what the targets are here, let's take a look at some of these different ways of finding these different kinds of life. So first of all, looking for life within our solar system. And I'm kind of partial to this one because I'm a solar system guy myself. So we've been looking for life in the solar system using telescopes, spacecraft orbiting around planets and moons, and increasingly in situ, actually landing on the surface, particularly in the case of Mars, and then really poking around and trying to find that evidence of life. The first thing to say is, no, we haven't found life that was so obvious that you could see it from afar. That's been very clear. But oh, and then there's the meteorites, right? Because occasionally we do get these things hitting us from elsewhere in the solar system, and there is a hope that, as with ALH 84001, maybe there will be evidence of life in one of those. The philosophy here is follow the water. Look for the places where there is liquid water in the solar system. There's one exception, which I will mention in a little bit, but that tends to be the guiding principle. And as I said, this has become a big focus for NASA now. And it's amazing how many of NASA's missions, their spacecraft have included looking for evidence of habitability, looking for evidence of life. This is now really become very part of the culture there. There's also kind of a big philosophical point with this one. If life formed twice in our solar system alone, that means that it's not just that life forming on the Earth was this 1 in a billion chance, and it probably only happened 1 or 2 other times in the galaxy, or if at all. If it happened twice just here, then the galaxy is crawling with the stuff. Okay, it's got to be everywhere. And so that would make it a really powerful thing, even if we just found bacteria on another world in our solar system. That would be enough. That would really completely define our picture of life in the universe as a whole. So that's a big thing to keep in mind. Okay, well, let's look at some of the targets here, because we can talk about some of our specific targets for life, and there's some really interesting things about each one of them. So Mars, okay, we've been looking for life on Mars for well over a century, almost a century and a half now, frankly. And yes, often we've been better at fooling ourselves than not. However, it continues to be a major focus, as I said, and so if you look at the mission statements for the Viking missions, the Spirit and Opportunity rovers, the Phoenix lander, Curiosity rover, Perseverance rover, there's elements about looking for habitability, looking for life in all of those missions. So this is a big part of what folks are doing. One of the key things, though, is that in the case of Mars nowadays, most of the focus is not so much on life today as what was Mars like in the past, and could it have been more habitable in the past? So this is kind of the basic assumption, is that Mars in the past, like when life was starting here on the Earth, Mars looked like it might have been a lot more habitable than it is today. And so that's what's driving a lot of this, is that not so much that it looks great now, but it used to be, it might have been a lot better. So most of the work then looks for either chemical or physical evidence of past biology, of looking at what was Mars like many billions of years, billions of years ago, literally, and maybe even are there any microfossils? Um, there is a few things happening now that have sort of tweaked people's interest. There's methane that's coming up from the interior at various times, and some folks have wondered if maybe that's being produced by life. That's still sort of a shaky one, but it's definitely a thing that's of interest. So the promise here is that Mars has at times had what might have been the most Earth-like environment in the solar system, particularly at the point in time when life was starting on the Earth. So if life was starting here, why didn't it start there too? Maybe it did. That's sort of a lot of the reasoning that's going on here. And of course, Mars having died off geologically, it's hard to, it's still easy to find what was there billions of years ago. Mars doesn't hide its past the way the Earth does. The challenge, well, Mars is a nasty place right now. And so that's why people are doubtful about it. It's a very harsh chemical environment. There's also some evidence that the times when there was water on the surface, a lot more water on the surface of Mars, that it may not have been long periods, billions of years of just of nice, stable bodies of water. It may have been sort of short periods of short wet periods that then dried out very intensely. So yeah, Mars, and I'll say, depending on who you talk to in the Mars community, some folks are really optimistic about what it was like in the past, and some folks are really pessimistic. And both sides are very knowledgeable, and so it's sort of the interpretation of the data they got that's going on there. Ocean worlds. This has become a term of art now within the field, and this refers to worlds that have an ocean, but more specifically to those outer solar system moons that have liquid water underneath a surface of ice. And so this includes worlds like Jupiter's moon and Europa, rather, Saturn's moon, Enceladus, also Titan. I'll say other things about Titan in a few minutes, but Titan actually does have liquid water below the crust there too. So in some ways, these are worlds that really do meet all of those criteria for life. Energy sources, there's plenty of organics in that part of the solar system. There's certainly lots of liquid water. Europa has many times as much liquid water as the Earth does. So it seems like the conditions are there. So this, one can might start with the assumption here of, well, if you've got the right conditions, you should have life, right? You got the mix of ingredients. Why not? And that's kind of been a working assumption for a lot of the folks studying these worlds now. Certainly, there is plans for most specifically the Europa Clipper mission to go to Europa and try to study that one. And there's talk of other missions going out to the Saturn system to understand those worlds better too. So maybe those could find evidence. The promise is, there's a lot more water than the Earth. If you can have life on the moon, around the moon of a Jovian planet, then suddenly you could have life in so many more places. You don't have to be stuck in a habitable zone terrestrial planet. That you get many, many more worlds to play with here for life to get started. The challenges, this is a low energy environment. We're a long way from the sun. Yes, you can get energy from internal heating with these worlds, but it's not nearly as much and not nearly as intense as what we get from sunlight. So that puts a real limit on what life could do. It's also just very hard to study because, of course, all the action, if it's happening, is happening below a thick layer of ice. Now, there's a chance that we can get around that with Saturn's moon Europa, or sorry, the moon Enceladus, sorry, because Enceladus has these wonderful geysers that blast the interior water out into space. In fact, it's what makes Saturn's E-ring is made from that. So we've already actually flown one spacecraft. Cassini flew through one of those geysers at one point, but it wasn't really designed to look for this kind of thing. There's talk of trying to get a spacecraft that is really designed to look for evidence of life, to fly through some of those geysers and see what it could find. Okay, and then there's the Titan lakes, because in addition to water somewhere deep under the crust, Titan also has the only other lakes in the solar system. The only problem is they're not water. They're liquid methane and ethane, and they're mostly near the poles of the planet. And yes, the Titan atmosphere also has some really interesting, what we call non-equilibrium chemistry. There's a lot of methane in Titan's atmosphere, and we don't know why, because honestly, it shouldn't be. Methane shouldn't last. And so that's got people thinking, well, you've got a liquid. Yeah, it's not water, but maybe you could base life on some sort of organic solvent rather than on liquid water. And so this makes Titan a bit of a dark horse candidate as far as the search for life goes, because there's a lot. That's a big ask. That's a big assumption to be making. But if it does, once again, what it opens up in terms of the possibilities are tremendous. There certainly are missions planned to go to Titan, particularly the Dragonfly mission. That's sort of just in the very early stages right now, but that might be one that is expected to land and travel around on the surface of Titan. So maybe it can find some sort of evidence of something alive in those lakes. You've certainly got the organic materials. If you could have life without water, this would be the place to put it. It looks good that way. But we have no idea how you have organic chemistry without water. How to make it work with the level of complexity that you can actually have a living organism. And a lot of biochemists who don't think it's possible really say, no, there's no way to make the energetics work. But there are also some who are saying, no, we can find some pathways to make this happen. So that's a thing that, as I say, it's a dark horse candidate. Okay, so those are some of the options looking for life within our solar system. Let's go outside the solar system now. So here we'd be looking now for biosignatures on exoplanets. So we're looking for evidence of life on these planets around other stars. Now that's a much harder thing to do because we can't go there. It's too far away still. So we have to look from afar. And the way we do that, and we focus, I should say, on the terrestrial planets. So finding life around an ice-covered Jovian moon, that's just completely out of our ability to do right now. But looking for planets like the Earth, looking for terrestrial planets in the habitable zone where you could have liquid water at the surface, that's beginning to be within sight. So we do this by using telescopes, Earth-based or in orbit, orbital-based telescopes, either seeing the planet directly, we're not quite there, but we're getting there, or looking for transits where the planet passes in front of its star. And that's the mechanisms that we use to really study these planets. And so I'm going to talk about 3 different types of biosignatures that we can look for on these planets. These are, first of all, the gaseous ones, in other words, the things in the atmosphere. We observed this, it's a really neat technique called exoplanet transits. And so what happens here is that the planet passes in front of the star. And as it does that, a little bit of the planet's atmosphere blocks a little bit of the sunlight, but that sunlight partially passes through that atmosphere. Kind of like the way when we look at a lunar eclipse and we see that the moon looks red because the sunlight has passed through the Earth's atmosphere and it's been redded because of scattering. Another thing that can happen is that atmospheric gas will also absorb some of that light, and we can then study that through spectroscopy and study the gases that are present in the planet's atmosphere. And so our assumption here is that life will alter a planet's atmosphere. And we know that happened on the Earth. So that's not too big of a jump there. So there are different gases that we can look for to say, if we find this, that's a strong candidate for life. Although they're at varying levels of strength. And a lot of it depends on what else is in the atmosphere. Oxygen has long been the favorite, and the oxygen byproduct ozone, because that's really the most obvious thing that we see in the Earth's atmosphere that was produced by life. So that's a promising option, but there may be a way of doing that, although it takes a fairly specific set of circumstances to do that without biology. So looking for oxygen in an atmosphere is definitely a good candidate. Methane, on the Earth, methane is produced by biology, but it may not be true everywhere. And again, that's one that's a little more problematic. We're looking, in fact, at an atmospheric spectrum that has methane in it. It's fairly clear that in the spectrum, but it's not a terrestrial planet. It's a Jovian. Methane in Jovians is a lot more plausible than methane in terrestrials. We see that in our own Jovian planet. So that's probably not as strong of a biosignature. Nitrous oxide is another one. And I'll say I could extend this list a lot further. I'm not going to, but there's a lot of different things that people have proposed. With most of them, you have to say yes, but it depends on what else is there as well. But these are the kinds of things we look for. But we have the technology to do this now. So people are searching for these gases in exoplanet atmospheres now. So the promise here, well, we know life modified the Earth's atmosphere. So this could be a very quick and easy way to find good evidence for life. The challenge, as I say, there may be non-biological ways of making some of these gases. So you have to be very careful that you don't just look at, say, I saw that gas, but also that you saw enough of the other parts of the atmospheric chemistry that you could say, yeah, and there's no way you could get this naturally just out of this mix of gases. Okay, what about the surface of the planet? The trick here is you can't really see the surface when we see a transit event. So we have to actually see the planet itself. And so we have to have a direct observation. But here the assumption is biological processes may be able to produce spectral features, things that we could see in the spectrum and the reflected light of the planet if we can get a good enough image of it. And this could include things like photosynthesis, for example. On the Earth, there is actually a very strong spectral feature that we've seen with our own spacecraft flying past the Earth, that comes from the fact that plant life, algae, and so on go through photosynthesis. And you can argue this one back and forth. Well, if you don't happen to be using chlorophyll, does that still work? The folks who study this say, yeah, because the energetics of just turning light into usable organic compounds put some real limits on what's possible here. And so there are certain spectral features like this red limit that people tend to talk about that may actually may actually be a strong indicator of photosynthesis going on. So the promise here, well, this may not only let us detect life, it may actually let us detect an actual biological process going on a planet. The challenge right now, we can't do this. Okay, we cannot directly image a terrestrial planet within the habitable zone of its star. It is hoped that the James Webb Space Telescope will fix that problem for us, that they may actually be able to do that. As with all things with James Webb Space Telescope, I will believe it when I see that first spectrum come down, when I see that first image come down. Until that's launched, until that happens, we just have to hope on that one. Okay, the third category is what they call a temporal biosignature. And this can be something that's either in the atmosphere or on the surface, but that is varying with time. And that indicates because of biological activity, typically what we think of as things that are seasonal. And so we're looking for signs of seasonal change on a world. So examples of this include the Keeling curve. This is something that we, in our own atmosphere, you may have heard of the Keeling curve. It's really what's one of the first big pieces of evidence that that carbon dioxide was going up in our atmosphere over years. But if you actually look at the amount of carbon dioxide in our atmosphere over just a single year, it goes up and down. Or in this case, we're looking at a 2-year cycle. And that's because of changes in photosynthesis on the Earth. And so that changes the amount of CO2 in our atmosphere. And yes, it's not a big change. You see, it's a few percent there, but that's enough that that might be measurable. So that's certainly something that one might look for in an atmosphere, is that change in a change in gas abundance with the seasons. Another one is vegetation changes. And so this is something that again, we know that on the Earth with seasons, many types of vegetation change, which changes the color of parts of the Earth's surface. That's a thing that you could certainly look for once you have direct imaging of a planet again. So the promise, again, this may let us see evidence of biological processes going on a planet. The challenge, well, you have to be really careful to make sure you're doing this right, because we have been fooled before. And of course, as I say, we need that direct imaging. We can't do this just with transits. But those some of us who are old enough remember occasional talk. Mostly when I was reading older books from the 50s, there were books that would talk about how, well, we see color changes on the surface of Mars, and maybe that represents plant life going through the seasonal change. No, it wasn't. It was dust storms. Okay, so we do need to watch for that kind of thing. Okay, so now these are some of the ways to look for. We talked about some of the ways to look for just any kind of life. What about intelligent life? And I want to start with looking for intelligent life outside of our solar system. And the first category I want to look at is electromagnetic signals. So the assumption here is that technological civilizations use some kind of electromagnetic signal to communicate, or through various other ways. And when I say electromagnetic, yeah, that could be radio, that could be microwaves, that could be visible light, that could be X-rays. Okay, so we could be talking about almost any part of the electromagnetic spectrum here as a means of communication. And then you can look at different ways, different things that might be going on that we might tap into. The first one, and what might be the nicest one to get, would be deliberate signals. That is somebody sending out a message either directly to us, which would be a little interesting, or even just broadcasting out saying, is anybody out there? Something like that. That would be really neat. I don't think anybody's holding their breath for that one, but it certainly is a thing to be looking for. More likely is some sort of leakage or just people broadcasting and not caring the fact that it's going out into the larger universe. We've certainly done lots of that. And so whatever means of communication you have, there are probably going to be a certain amount of that energy, often most of that energy, that doesn't go to the recipient, but rather just gets sent out in the broader universe. So that's certainly a possibility. Something that isn't really communication, but which is closely related and maybe actually the most detectable is radar. A high powered radar signal can pack a lot of punch. You can get a lot of energy, and it's often very directed. So if you've got a radar beam that happened to pass your planet, you might notice that. Often even when you didn't pick up, because often these are some of the strongest signals that we produce. So that's another area that you could look for there. So the promise here, well, if we found what was clearly a carrier wave or clearly a radar signal, it would be unambiguous, or even a laser transmission, for example. That would be very unambiguous. Nature doesn't do those things, not in the kind of narrow beam approach. So that would be a really strong piece of evidence that you were looking at something intelligent. And it might even carry information. So we might actually learn something about these people, which would be really interesting. The challenge, there's a couple. One is what they call the attenuation problem, or the 1/r² problem. It's just that, as when you double the distance, the signal is only 1/4 as strong as it was before. And when you start talking about interstellar distances, that drop off in signal gets to be a big problem. And it's not clear. You would need to have some really strong transmitters before that would be you'd have a real chance of finding a signal that's going that can be observed more than a few light years away. So that really limits how far you actually have a good chance of picking up some of these things. The other is just what they call the needle in the haystack problem, which is just that the parameter space is large. Okay, we're talking about all of the radio, microwave, visible, you got this whole vast electromagnetic spectrum. You have different time regimes because, depending on how long you're listening, you may or may not notice the signal. And then you have the different directions in space, right? You've got the entire universe to point your radio telescope at. That makes it, and so far we have not really explored very much of the universe this way. And it would be really surprising, frankly, if we found something with the little bit that we've already done. So there could be all kinds of communication going on out there, and we didn't happen to tune in at the right frequency. We weren't looking in the right direction. And that's a really basic problem we have with this approach. Okay, well, what about some of the other techno signatures, other things that a civilization might do that we could observe? We think there may be many ways that a civilization might actually impact its environment. One that we know, unfortunately, rather well is pollution. You can look for evidence of in that when you're taking the spectrum of a planetary atmosphere, you can look for evidence of compounds that you don't think should occur in nature. Chlorofluorocarbons is one that's been kicked around as a possibility that somebody might notice in our atmosphere, or at least would have for a little while until we stopped throwing so much up there. There are definitely compounds that a technological civilization is going to produce that you really don't expect to appear. And it's not just in the planet's atmosphere. You could also look at the star's atmosphere, because we could certainly imagine a civilization using a star as a dumping ground for stuff that it doesn't want. And if it's just a little bit of stuff, you probably won't notice it. But if you start getting into large enough quantities, especially of things like some of these heavy elements, the heavy metals that are very rare in the universe, anyways, particularly radiogenic ones that you might be creating yourself, at that point, that's the kind of thing that could very well show up in a stellar spectrum. And there are a couple of stars where people have actually asked that because they really did have some unusual spectral signatures. So far, what we're finding is no, we can think of other ways of making the things that we're seeing there. But those are very limited ranges. You can, if it gets too far, if you see too weird a mix of heavy metals in an atmosphere, you're going to have to say, we don't know how to make that. And that's good. That becomes an interesting techno signature. What about artificial light? Okay, we astronomers, we know that we light up the night, perhaps a little more than we would like. But you can start asking the question, how much artificial light would it take to show up on the night side of a planet? And actually, some folks have done that calculation. It turns out that with the James Webb Space Telescope, looking at a nearby terrestrial planet, no, they wouldn't be able to see the Earth. If you had a civilization that was putting out about 1,000 times as much light as the Earth is, yeah, we might actually be able to see that. Okay, that's a big jump between what we do and 1,000 times what we do. But what that means is that we're not that many orders of magnitude away now from being able to see this. We're not there yet, but we could start thinking about what it would take to actually observe a civilization maybe only 10 times as bright as us. How long will it be till we have the technology to see that? That's becoming the kind of question one can reasonably ask. Propulsion systems, and yes, yeah, maybe we're talking about rockets, but I want to mention another kind of propulsion system that might actually be very visible. You may have heard of something called Operation Starshot. This is a suggestion that we could send a solar sail to Alpha Centauri if we took a really, really powerful laser and basically pointed it at that solar sail, and we could push that thing up to 0.2 times the speed of light. Well, if anybody actually did that, that would be really bright. And if you happen to be in the beam of that laser, you'd have a good chance of noticing it. So that's might be the kind of propulsion system we would actually have some chance of seeing. So the promise here, among other things, we can look for all this while we're looking for biosignatures. So it doesn't require a big separate search. This is the kind of things we're going to be looking for anyways. So that makes it kind of nice. It really lets it piggyback on other searches we're doing. The challenges, like a lot of these are ambiguous. A lot of them are tough to be confident of what you're seeing. Yeah, if we saw a gigawatt laser pointed at us, we'd be pretty comfortable with that one. But some of the other ones, it would take a lot of work to convince yourself that what you had was actually technological. Okay, and then the last category I want to mention of things we might look for on exoplanet civilizations are what we call megastructures. And the idea here is that a very advanced civilization could very well start building structures that were planetary, even solar system scale objects. And that those are things we could find. And so this goes back originally to Freeman Dyson didn't originate this, but he popularized this idea of a Dyson sphere, which is basically a sphere completely surrounding a star. And the reason for it, what Dyson's argument was here is that, as civilization grows, it demands more and more energy, and eventually the civilization wants to use as much of the star's energy as possible. And so in order to capture that energy, you basically have to surround the star. And so that's where you get a Dyson sphere. And that's an idea that's been kicked around, and many different modifications of it suggested, including swarms of bodies instead, or partial structures. Larry Niven, if you're a Larry Niven fan, he talked about ring worlds as a ring of matter around the star. Another variation on that idea is what's called a bishop ring. A bishop ring is is basically like a ring of material that's spinning fast enough that basically you can capture the atmosphere and have people walking around on the inside of the ring. And these things can easily be many thousands of kilometers across. In fact, the bigger they are, the better they work. So that's becomes these are certainly imaginable structures that a civilization that's around long enough might very well decide to do. Okay, so how do you find these things? Well, you can observe them a couple of ways. First of all, you can observe them through transits, things like ring worlds or bishop ring. As they pass in front of their stars, they actually block a significant amount of starlight. And since we're already searching for planets this way, that's definitely a one that you could find easily. Something like a Dyson sphere, you would actually see because you still have to have all that energy eventually has to come out as waste heat. And so if you look for something that looks like a star in that it's putting out as much energy as a star, but it's all coming out at way out in the far infrared rather than in the visible spectrum, that's what a Dyson sphere would look like. And so that would be another kind of object that you might look for, and that we certainly have the technology to do right now. And that's the key thing with these ones, is that we can look for them today. And there are a few minor searches being done. And as I say, you might pick it up on the way while searching for doing other kinds of astronomy. But we certainly have the technology right now to see these kinds of objects. The challenge, well, we've already also had a number of false positives. We've had a number of cases where people thought they might be seeing a Dyson swarm or a ring world. And then no, it turned out it was a disk or a bunch of debris or a dust cloud or something. So it's, again, you got to be careful not to get fooled with these ones. Okay, so the last big piece of this talk, and in some ways the part I was most hesitant to do. In fact, when I first drew an outline, I almost didn't put this part in. Looking for intelligent life within our own solar system. And this comes down to that classic question: are we being visited, or have we been visited? And in the scientific community, this is by far the least popular one. This is the one where you could still get yourself into trouble by saying, look, this is what I'm doing, because there has been such an overwhelming number of false positives, of fakes, of mistaken identities, all kinds of things. And, it's a field that's swamped with that. And it's very hard to pull from that anything that's usable. So I think the thing to do then, the thing to ask is, are there scientific approaches to this that we can make to ask the question, have we been visited or not? And how would we go about doing that doesn't just rely on your cousin's shaky cell phone video type of thing? What are we doing here? So let's start with monitoring our own inner solar system. So we're watching our inner solar system now in great detail. It's pretty hard for anything bigger than 1 kilometer to come through the inner solar system without us seeing it. You can imagine the orbits where they involve close passes by the sun and then coming straight out at us, but it's a pretty limited set of phase space now where you can do that. And we see a lot of much smaller objects now. And we've been successful in that we've found at least 2 different interstellar objects that have passed through our solar system in the last few years. And we think this is just the first of many that we're probably going to find as time goes on here. Now, as I say, that we really are monitoring what's happening. So the objects that we've seen, both the Oumuamua and Borrelli, are somewhere in the sort of 200 to 500 meter size range. As I say, we saw them. We know that they're interstellar. They clearly came from outside our solar system. They were moving way too fast to be solar system objects, and they rolled on back out again. Well, in the case of Borrelli, kind of broke up instead. So this is I'll just for context here, we're starting to get into Starship Enterprise size range now. Just so yes, this is we're starting to talk about plausible spacecraft here. Greater than 1 kilometer. Well, yeah, generation ship type things might be in that range. But yes, these are things that we could that we you could talk about, as I say, as being possible spacecraft sizes. When we talk about near Earth space, within about 1/10 of an AU, we see a lot more. We see things, possibly down to about 10 meters. Certainly within a couple of tens of meters. There's a pretty good chance of spotting those things. And honestly, if I were traveling in interstellar distances, I wouldn't want to be traveling in anything smaller than a few tens of meters across. I mean, let's face it, that's not very big. So yeah, so unless something is sort of very deliberately hidden, we're probably going to see it coming. That's the first thing to appreciate, is that we're now watching that closely. So, and I'll say the assumption here I'm making is that alien spacecraft are observable. They're not so effectively hidden that we can't pick them up at all. That's, I think you got it. Otherwise, you're sort of, yeah. Otherwise, you start having to wave your hands and to talk about magic almost. So but let's look at what else we can do. We are also monitoring the Earth, and I think when you stop and think about how many different ways we are monitoring the Earth, we have weather satellites, some that watch continuously, some that look at specific parts of the globe, some that look at some that look at the long term, some the short terms, in all different wave bands. We have a number of different Earth imaging satellites that are just really taking pictures, looking down on the Earth from space. Both government and private. There's at least a dozen different private companies now that have different Earth observing systems that they're running. There are, of course, all those spy satellites, and a lot of governments have those. And there's even a whole set of satellites that are specifically enforcing various nuclear treaties, and they're looking for a lot of the same kind of things that you would look for if you were looking for a spacecraft entering our atmosphere. And the countries that are doing this, when I look down the list of all of, and I don't think this is a complete list, but it gives you an idea. So Brazil, Canada, China, the European Space Agency, France, of course, has also got its own. India, Israel, Japan, Pakistan, Russia, Taiwan, Turkey, and the US all have Earth surveillance satellites of one sort or another, and often many different types. So this is something that we're watching ourselves pretty effectively here too. It's going to be hard to get in. And then, of course, there's all the ground-based stuff, things like air traffic control radars, defense radars, which are looking very closely at anything coming in. And then there's this. So one thing when people ask me about UFOs and do I believe in UFOs, I'd like to point out, I grew up in the 70s. And at that time, UFOs people were really excited about UFOs. And the best evidence were these sort of very shaky Super 8 videos that show a little dot vibrating around in the sky, or very blurry photos that hard to tell what they were. But what do you expect? I mean, if your best camera was a Kodak Instamatic, and or a little maybe a Super 8 camera, most people didn't even have that. Yeah, sure, you're not going to see much, but what about now, when there are 6.4 billion smartphone users, people who have things like this, that can, with high resolution digital video and still cameras on them. And our best images are these, shaky videos and a couple of, blurry photo of something that may or may not be a dot in the sky. I mean, at this point, if we were seeing anything real back in the 70s, then we should have it. Then, we should have these things very well documented by now, and we don't. So we're doing a good, we got the technology now to keep a very close eye on the Earth, and we're still not seeing very much. So the promise here, I would say, is that, if an alien wanted to, they could make it really easy for us here, right? I mean, they could show up and show off the kind of technology that would, okay, yep, that's real, we got it, no problem. It would not be hard if they wanted to. The challenge is this does depend on them visiting us, and it depends on them visiting us in a fairly short window of time. Remember, we've only been watching for a fairly short period of time. So what can we do about that? Well, there's one other approach, and that is to look at, well, what about alien artifacts? Okay. Here you make the assumption that maybe aliens have actually visited at some point in the past and left some piece of technology that was clearly not non-human. Of course, you may recognize this as the plot of 2001: A Space Odyssey. And of course, numerous bad documentaries as well. The problem, this is something which, yeah, we've thought about, many people have tried. We haven't found anything yet. We really haven't. But we could certainly, there's a possibility that as a byproduct of our exploring our solar system, we might come across something that would fit that. I don't think anybody's sort of seriously doing searches for alien artifacts on other parts of the solar system right now as such. But yeah, certainly if you see something while you're mapping Mars, or looking at the asteroid belt or something like that, yeah, that's it. If it shows up as an anomaly, people are gonna start digging into it. The promise, well, of course, it avoids that whole limited time problem. You then have the whole history of the solar system, which the visitor might have arrived. But it may be really hard to recognize an alien technology, especially if it's been sitting for a while, from any distance. I mean, yes, if you actually dug one up like this one in the movie, yeah, then you might that might work. But we're a long way from doing that in most places in the solar system right now. So I think we're still got a ways to go there. I want to wrap up with two thoughts. First of all, would we recognize an alien intelligence? And I throw that out because the picture here on the right, the trilobite there, that trilobite was one of the most advanced creatures on this planet a few 100 million years ago. I don't think that trilobite would understand very much of what humans do, or even necessarily recognize humans as anything alive, honestly, or even have a concept of alive. And yet, a few 100 million year gap in time is just not very much, astronomically speaking. It is at least as likely that that a alien that we ran into would be a billion years ahead of us. And would we have any idea what they were? I don't think we would. I really don't. I mean, we'd be like that trilobite sitting there saying, yeah, but can I eat it? No, yes, that's it. So I think that's a thing that that we have to keep in mind here. We could probably only recognize alien intelligences within a certain window of time, and beyond that, we're not gonna even know what they are. So let's finish off. Who do I think is going to win? Well, let's take a look. I think any of these approaches could. I think any of these approaches could be the first way we find life. I think solar system exploration within the next couple of decades is going to put some pretty serious limits between upcoming missions to Mars, to Titan, to Europa. I think we're going to start being able to pin down, we're going to start saying yes or no with a lot more confidence on those worlds than we can right now with things that are already in the works. With something like James Webb Space Telescope, and if not James Webb, then probably the next generation down the line in exoplanet studies, we'll certainly should be able to find biospheres in nearby planets, nearby star systems. So that's, again, we're talking about a fairly short time scale. That's a thing that, you know, I'm no longer thinking, oh, someday. No, this is, you know, now I think we're going to start having answers here pretty quick on these ones. So in fact, if I'd go so far as to say that if we don't see life from any life techniques within the next few decades, it may tell us that life, or at least detectable life, is very rare. I mean, I think we're going to have, if we don't start finding something soon, that's the thing we're going to have to face, because we're starting to get to the point where we're going to start putting serious constraints on what's possible out there. Intelligent life, much harder to put any kind of a guess on, because it depends on too many assumptions about that intelligent life that we really can't test. We don't know, and so it's so much harder to put any kind of constraint on that right now. So that one I kind of have to throw up my hands. But I think what I will say is, ask me in 2040. Let's see what we've got. And that's my talk. Any questions?
Yeah, I have a question. First of all, I think that you did an outstanding job covering this particular topic because it's wide open, obviously. So you've defined more or less the realm of possibilities for the detections and possibilities for life. Obviously, this topic is wide open for not only getting false positives, but also false negatives, because we basically have one example of life, and that's here on Earth. So when you open up the possibilities, when you are looking at some signature that is not fitting what you think is a signature that should be for life, you're going to miss it. And I think that in general, you know, just listening to what you were saying on the methods that were being used and everything, is that most of the work is being done looking for not any life, but any Earth-like life. And that's only natural because we only have one example. How are you going to look for you know, something that's based on methane or something if you've never had any one example of it? But one of the things I have a question about is with one of the tenets that you have identified, that is the one that where you said, if you have the right conditions for life, it will start. And my question is do you think that the conditions on Earth today are conducive for the start of life? And if
Today,
so,
no.
no,
Today,
okay.
no, it's a terrible environment today.
Okay, so the rest of my question
We got this
is,
nasty oxygen stuff in our
I
atmosphere.
know, okay.
You'd never
So
want to start life in an atmosphere like ours.
that was the rest of my question is, why don't you think that it's a good time for starting life on Earth? Okay.
Yeah, no, oxygen. If you were trying to start life from scratch, oxygen is a scary thing to have. You need some really fancy biochemistry to turn oxygen into something usable, and that's, you wouldn't want that as your starting point.
Okay.
So that, I mean, right away. There's also, just in terms of abundance of just general organics, and you know, the ability that we don't really have. You know, we've locked up most of the organics in forms that would probably not be very conducive to life as well, to life starting. It's great if it's there, if you're already alive, you can make use of it. But if you're trying to start it from scratch, I don't know. I don't think we've got a good environment for that. But the oxygen, that is just a nasty chemical. Stay away from that stuff, man.
Okay, thank you.
Okay. Yeah, if you want to ask a question, go ahead and unmute yourself.
I should throw in that while I did this talk, a lot of what I've said came from conversations with Joanne, my wife there, who's actually currently teaching a Life in the Universe class over at Chaffey College. So this is, a lot of this has come from us talking back and forth, and me learning a lot from her in terms of what the issues are, and her pointing out, look, you should see this talk, or you should read this paper, because she's really been doing a lot of the research for that course.
Okay, I'll unmute myself for a second then and just put in a plug. In this course, since this is the first time I'm teaching it, I'm using an awful lot of other people's materials. And if you folks are interested in something that's very, very available, the astronomer, the University of Arizona astronomer, Chris Impey, has a MOOC, a massive open online course, and I cannot remember which of the big platforms it comes from, but Impey is IMPEY, and if you search on him, oh, in fact, you don't even have to join the course. He even has all of his lectures, and they are extensive. I mean, it is truly a college course's worth of lectures. Posted, I think, in the International Astronomical Union has a working group on, can't remember whether it's Life in the Universe or astrobiology, but search on that, or just shoot me a line and I can send you a link. And it is really an extensive, if you want the 50-hour commitment to listening. That isn't quite the way I would do it now that I've listened to it through and tried to make multiple choice questions about all of it. I see the way I would do it differently, but it is really good in his way. And I would certainly encourage anyone who's interested to go ahead and start looking at the Impey lectures. My main criticism is he needs more pictures, but that's a small criticism, right? So go ahead, Chris. I'll put Chris Impey in the chat.
Okay.
Could you talk a little bit about the perhaps evidence of life in the atmosphere of Venus?
Sure. Yes. So that was an announcement last year that they found phosphine in the atmosphere of Venus, and phosphine on the Earth is produced through biological processes. Unfortunately, what hasn't made the news is that since then, that phosphine discovery has been thrown into pretty serious question. There's now been a few different groups who've been looking either at their own data or even at the same data that was originally used and saying, no, that's not what you're seeing. It's something else. And so that's, yeah, so unfortunately, no, that one's not holding up terribly well. I think there's still, and I debated over whether to put Venus and the Jovian planets in there. I figured the talk was getting long enough. I had to cut some things. I mean, but you certainly could say, well, there's a possibility in the clouds of Venus and the clouds of the Jovian atmospheres for something floating in those atmospheres. There certainly are places where the conditions are reasonable, where water behaves as a liquid, and you've got you might have the organics. So yeah, it's there, but right now there's even less evidence for those than the others. So I think that's why I decided, okay, we don't need to add that one to the mix yet.
Okay.
Glad you made it, Sammy.
I found it interesting to think of native cultures as you were talking about what could be observed, and that intelligent life and signs of technology, and you think back a couple of 100 years and you wonder if technology is the way things are destined to go, or
Yeah.
what Native Americans do. Is there any evidence of what they did at all that you could observe from elsewhere?
Well, I mean, honestly, the Earth was certainly not observable, but did not have any obvious technosignatures before, certainly not before the Industrial Revolution, and I think debatable until at least the 20th century, well into the 20th century, anywhere on the Earth for any culture.
Yeah.
And so, yeah, I think that's, we do have to keep in mind that, and this gets back to what we were hearing before about false negatives. You know, we don't even have to start thinking about obscure life. You know, for most of human history, well, we would not have been observable as an intelligent species.
Right.
And so that's a thing that now one of the arguments I've seen is that, yes, but that's because we're only looking backwards. It may be that, you know, we'll be a technological species that's around for 100 million or a billion years. Maybe. We have no idea. But yes, I think we have to recognize that that even this approach, the most optimistic approaches, it's still going to miss a lot of intelligent species. Absolutely.
Yeah. You've got that window, or does technology last that long?
Or does it last? Or does technology become invisible? I mean, one could imagine, there's a lot, there's a lot of things of directions you could imagine with technology where rather than becoming more and more obvious, you actually becomes less and less obvious. That it becomes more efficient, that has less, you're generating less waste heat, less waste light, you're not creating as much pollution, your communication is all much more narrowly focused, so you're not broadcasting everywhere. I mean, at that point, you become invisible again.
Right. Yeah. In a totally different way than you were before.
Optical fibers.
Joseph, I'm glad you like the talk. So question. Okay, so Joseph was asking in the chat a question about discrediting claims from individuals, and that's always a really tricky one. And I don't really know the best way to handle that. I think a lot of it becomes is something you have to do on a case-by-case basis, because people get really wrapped up in this and can build their entire identity out of it. And going after them for that can then be itself creating as much of a problem as it is solving. I think what you do need to do is simply focus and try to sort of teach the idea of focusing on the evidence, on physical evidence, on things you can really test. And I think that's really a more important and more productive approach than sort of chasing after, somebody who says, I was abducted. I know I was abducted. Okay, look, that you can create, like I say, you can create more problems for yourself than is worth if you try to make that what your focus is.
Dave, I have a question. It seems like in the search for intelligent life, we have two assumptions that we're kind of stuck with. One is a limit of communication by the speed of light. We don't know of any technology that can communicate faster than that. So we're stuck with that. And also time travel issues. We're stuck with that assumption. I think we can't get out of that box without getting a little crazy. So it seems to me that for us to receive a sign of intelligent communication from space, to detect that would require a focused beam of intelligent life coming to Earth. Just a random, like they used to talk about the radio signals from I Love Lucy episodes in the 1950s, spreading out into space would be so diffuse before they got to any other intelligent life that they wouldn't be responding to that. They couldn't pick it up, probably. And same for us. If a remote civilization communicated randomly, we wouldn't pick it up. But if they focus something at us, we might be able to pick that up. But then that means that they would have had to have aimed at Earth at some point in time. And you would think that they would not have aimed at Earth before, as you just mentioned, a technological stamp coming from Earth, evidence of technologically advanced civilization here. And therefore that limits us to maybe 150 light years away from Earth. that another civilization could detect us. And you know what I'm saying here?
Yeah. And that's a reasonable set of assumptions, although it's not an ironclad set. And I think as I say, it's a very reasonable set of assumptions. A couple of alternative approaches would be to say, is the assumption that, as you say, we have that 1/r² problem, the attenuation problem. But there's sort of a range of options between sort of full, say, 180-degree broadcast and absolute narrow beam focused on one world. You know, there's quite a range in there, and somewhere in there you could very well hit a sweet spot where maybe your high-powered radar, for example, which is a fairly narrow beam, pointed in one direction, and we just happen to be in that direction. And yet it's not such a small beam that the odds of it actually getting to you are become infinitesimal. And so that's kind of, you've got to balance out you got to sort of look at where those come out. And as I say, that depends in turn on your assumptions about what the technology of a civilization is doing, not just at our level, but say a century or 1,000 years or 1,000,000 years ahead of us. And you know, if you've got a Dyson sphere powering your radio, how does that change what your broadcast numbers look like?
But then you still have the question of why would they aim it even as broadly as to our entire solar system? Why would they aim at us before?
They wouldn't. We just happen to be in the way.
Oh, okay.
I mean, we're sending out high-powered radar signals in random directions in space.
And maybe
it just happens that,
yeah, maybe 60, 50 light years away at this point.
But my point is that we're sending those signals not because there's somebody we're expecting to receive it. It's just that that's the direction that happens to be going after it passed the plane that we were sending the radar signal at. Mm. And after that, it just keeps going for the rest of the universe. If there happens to be a habitable, an intelligent species somewhere in the way, maybe they pick it up.
Maybe they pick it up, but by that time, if then they respond back to us, you know, and we're long dead.
Yeah, but the point is, we're not the only ones doing that. There could be any one of a number of other species anywhere in our end of the galaxy who are doing the same thing.
Yeah.
That's where, and as I say, it's a numbers game, and we really don't know what the numbers are.
And we don't know if our detectors are strong enough to pick up these very highly attenuated signals. That are
Or are we going to just lose it in the noise? And that is and that's why I said, you know, this one, it depends on, looking for intelligent life right now, it depends on too many assumptions that we just don't know the answers to.
Fascinating. Thank you, Dave.
Okay.